What's up, Chem peeps? Who's ready for some free response practice? Get to bust out your art skills and draw some Lewis structures. The species represented above all have the same number of chlorine atoms attached to the central atom. 4. Part A. Draw the Lewis structure, electron dot diagram, of each of the 4 species in the boxes below. Show all valence electrons in your structures. Alright, I know there's a lot of different ways to draw Lewis structures. I'm going to work you through the way that never fails, and I encourage you to do the same. Start by counting up the total number of valence electrons you have to work with in your molecule. For GeCl4, 4 valence electrons from germanium, 7 from chlorine. Since you have 1 atom of germanium, it will contribute 4 valence electrons to the molecule. Since you have 4 atoms of chlorine, they will in total contribute 28 valence electrons to the molecule. In total, 32 valence electrons to work with to build your Lewis structure. Next, determine the total number of valence electron pairs you have to work with. Boom! Begin to build your skeletal structure with the less electronegative element in the center. Surround it by all the remaining atoms. Next, connect the central atom to the terminal atoms with a single bond. Subtract the number of pairs used to do that. Got 12 pairs left. Put those extra pairs on the terminal atoms first to complete their octets. Boom! Subtract the number of electron pairs that you used. Boom! When you've used up all of your pairs, check to ensure that all of the elements that follow the octet rule do, but be cautious of any exceptions. In this case, we are good to go. 1 point. I'm going to repeat that process for the remaining structures, but I'm going to speed it up a little bit. So for my molecule of SeCl4, I've determined that I've got 17 valent electron pairs to work with. I'm going to place my less electronegative selenium central, surrounded by my chlorines. Connect them all with a single bond to start. Subtract the number of pairs that I used to connect my central atom to the terminal atoms. Minus 4. We've got 13 electron pairs remaining. First, assign them to the terminal atoms, completing their octets. Boom! Subtract the number of pairs that you used to do that. Notice that this time I have pairs left over. If you have pairs left over, after you provide an octet to all the terminal atoms, place it on the central atom. Boom! Subtract. I've used all of my pairs. Make sure the elements that follow the octet rule do, but be cautious of those exceptions. In this case, we have an exception. Selenium has more than 8, but that's okay. Selenium can have an expanded octet because it's in the 3rd period or below on the periodic table. Thank you, empty d orbitals. Again, I know it may look a little funny, but use these steps every single time and you're guaranteed to come up with the correct Lewis structure. Let's keep going. Boom. In ICl4-, I've got 18 electron pairs of valence electrons to work with. Be cautious, this is an ion, a negative ion, indicating that it's gained an electron. So be sure to include that in your total number of valence electrons that you have to work with when building this Lewis structure. Again, the less electronegative goes central, surrounded by the other atoms. Boom. Connect the central to all the terminal atoms with a single bond. Boom. Subtract the number of pairs that you've used from your total number of electron pairs you have to work with. Got 14 pairs remaining. Remember, always put them on the terminal atoms first before you put them on the central atom. I'm going to distribute them so that each of my terminal atoms has an octet. Subtract the number of pairs that I've used. I still have pairs left over. Again, when you have pairs left over after you've distributed to the terminal atoms, put them on the central atom. Boom. I've used up all of my pairs. Alright, now I know these may look a little funny, kind of like your physics teachers, but this is where we get into some of those crazy shapes with the octahedral, trigonal, bipyramidal electron geometries. Trust me, use this system every time. It's a no-fail. 1 more. Let's do ICl4+. First, let's come up with the total number of valence electron pairs. Boom. Be cautious. This is again an ion. It's a positive ion, indicating that it's lost electrons. So notice how I've accounted for that when I've totaled up my number of valence electrons that I have to work with in this molecule. Positive ion lost the electron. Alright, once we've got our total number of valence electron pairs, let's build this. Less electronegative goes central, surrounded by the other atoms. Connect them with a single bond. Subtract from our total number of pairs. If you have pairs left over, which we do, add them to the terminal atoms first. Boom. Be sure to subtract the number of pairs that you used. If you still have pairs left over, then add them to the central atom. Boom. Again, check to make sure that we follow the octet rule, but be aware of those exceptions. Iodine, 3rd period or below, it's able to have an expanded octet thanks to those empty d orbitals. Final note I want to make here. Don't forget with your Lewis structures that are ions, be sure to enclose them in brackets and include the charge of the ion outside of those brackets. Boom. Not gonna take points from me this time, College Board. Not this time. All right, 4 beautiful Lewis structures drawn. Now let's answer some questions about them. You know they're gonna be fun because some of these shapes are crazy. Part B. On the basis of the Lewis structures drawn in Part A, answer the following questions about the particular species indicated. Subpart I. What is the Cl-GeCl bond angle in GeCl4? Let's go back up and take a look. Oh, what a beautiful structure. All right, now don't be fooled. The Cl-GeCl bond angle looks like it's 90 degrees in 2 dimensions. But no. Although Lewis structures are awesome and super helpful, it's often difficult to depict the true 3-dimensional structures of those molecules using just the 2-dimensional Lewis structures. Fear not, PhET has got our back. Check out this amazing simulation where you can turn your 2D Lewis structures into 3-dimensional beautiful works of art to help us understand what the bond angle is going to be in this 3-dimensional structure. So not 90 degrees. Remember, the electrons are repelling one another and they want to get as far away as possible. In a 3-dimensional world, they can get further away than 90 degrees. For regions of electron density, they can get 109.5 degrees away from one another. 109.5 degrees. Boom. Wait a minute. What if I don't have a fancy simulation to use on my AP exam? What am I supposed to do then, Boylan? That is a good question. Let's go back to our Lewis structure. You want to be comfortable counting up the total number of regions of electron density around your central atom. In this case, there are 4. And because you have spent 20 minutes every day for the past 2 years practicing these geometries, you know that 4 regions of electron density indicate tetrahedral geometry. And based on the extensive practice that you've done with the PhET simulation, in your brain you have already locked away that the answer is 109.5 degrees. Bottom line, you just gotta practice, put those things away in your brain. It's gonna be a great time. Subpart II. Is SeCl4 polar? Explain. All right, let's go back up and take a nifty look at our Lewis structure. Ooh. Now, when answering questions like this, it's a good idea to have the 3-dimensional structure imagined in your brain. And if you're having a hard time imagining, let me build it for you in a PhET simulation. Ooh. Here we are. SeCl4. Check out those lone pair of electrons and how they affect the geometry of this molecule. Do we think that this is going to be polar or non-polar? Is this molecule symmetrical? Do all the individual bond dipoles cancel out? Or is this molecule asymmetrical? Are we going to have a net dipole overall? That lone pair of electrons indicates most likely we are. Yes, the SeCl4 molecule is polar, because the lone pair of electrons on the central Se atom repels with the bonding pairs of electrons, causing a spatial asymmetry. Asymmetry of the dipole moments of the SeCl bonds. The result is a SeCl4 molecule with an overall net dipole. Now, if you're like, what kind of jibber jabberish is this College Board mumbo jumbo? Let's do it. Let's have PhET help us out. Imagine this lone pair of electrons was not there. Let's go back to, say, GeCl4. This is a non-polar molecule. Now, there is still dipole moments that are created by the polar germanium-chlorine bonds, right? But here, there's no lone pair of electrons on the central atom. This is a symmetrical molecule, so the dipoles cancel one another out, and we say that this molecule has no net dipole, aka it's not polar. Oh, but put that lone pair of electrons back on there. Oh, our world goes asymmetrical. Again, our dipole moments, or the polar bonds that exist or the dipole moment we'd be looking at if we were just looking at the individual bonds, do not cancel out. And they do not cancel out because of that lone pair of electrons that's interacting, repelling the bonding electrons, creating an asymmetrical molecule. Oh, all this mumbo jumbo is becoming so clear. But I spend like 20 minutes every night playing with the FET Vesper simulation. So, moving right along. Subpart III. What is the hybridization of the Ge atom in GeCl4? Let's go up to our Lewis structure. Once again, you want to count up the total number of regions of electron density, or electron domains, about the central atom. We have 4 of them. And then just think about the different hybridizations. We have sp hybridization, sp2 hybridization, and sp3 hybridization. Easiest way to figure this out, the number of electron domains has to equal the sum of the superscripts. So this is really S1P1, S1P2, S1P3. Go back and watch that vid on hybridization if you're confused. But the sum of these superscripts here would be 2, would be 3, this would be 4. I have 4 regions of electron density, so my hybridization is sp3 hybridized. Oh, so easy. sp3. Boom. I love the questions with no justification. Makes my life easy. Subpart IV. What is the geometric shape formed by the atoms in ICl4+? Let's check out the Lewis structure. Here we are in ICl4+. To come up with the shape of the molecule, shape of the atoms, the geometric shape. I've got 1, 2, 3, 4, 5 regions of electron density. But one of those regions is a lone pair region. Having trouble visualizing? Let's go to FET, our ICl4+ molecule. We want to know what shape do the atoms take, the molecule itself. All right, when I do this, I like to start with the total regions of electrons. And I've got 1, 2, 3, 4, and that one in the back, 5 regions. That means that the shape that my electrons take is trigonal bipyramidal. Oh yeah, 2 3-sided pyramids, one on top of the other. But I want the shape of just the molecule. Let's spin this sucker around. Maybe it's easier for you to see the shape. Oh, there we go, there we go. Do you see it? Do you see it? Trigonal bipyramidal, in which one of the regions is a lone pair, is called the seesaw geometry. Boom. Subpart V. What is the geometric shape formed by the electrons in ICl4+? Oh, we just answered this. Trigonal bipyramidal. Boom. And then finally, subpart VI. How many sigma bonds and how many pi bonds are in the ICl4- structure? All right, let's go check out this structure. ICl4- is here in pink. We've got 4 bonds. 1, 2, 3, 4. All of them are single bonds. And remember that single bonds are sigma bonds. But you could imagine how someone drawing this Lewis structure might, instead of putting these lone pairs on there, create double bonds or triple bonds. 4 sigma bonds, 0 pi bonds. Remember, you're only going to see those pi bonds in double and triple bonds. Boom. Also, one final point. Don't forget to say 0 pi bonds. You need to be very clear that you're not just leaving it out because you don't know. You know that there are 0, so be clear. You know the College Board. Kinda dense. Alright, and that does it for this vid. Have a fantastic day.